Welcome to this lesson on magnetism. This lesson is going to focus on the mathematics and the equations that model magnetism. So the first thing we're going to start with is a demo we've already seen, and that is current making a magnetic field. All right, we saw it happen. So let's look at the equation that models it. So we have a wire here that has current. All right. It's going to make a magnetic field all around here. Now there's a whole bunch of stuff in the direction of that, but we're just going to focus on the magnitude. All right, the direction can get a little complicated and it's hard to convey and work through video. So I have points A and point A and point B here. It would make sense that the closer that you are to a wire, the stronger the magnetic field is going to be. All right, so point A will have a stronger magnetic field than point B. All right. And remember, it's the current that is making that. So the equation that models that is this. B equals, this is called mu naught. It's like mu S, mu K, which is pronounced mu. And when you have a little zero there, it's called naught. All right, so B equals mu naught I over 2 pi R. Now, what do these things represent in this equation? All right, so B is the magnetic field. That's our new symbol for the magnetic field. And the unit of magnetic field is the Tesla, not named after the car, but named after the a famous inventor who lived in the early 1900s. All right, so how strong a magnetic field is given by how many Teslas it is. All right, we already know I is current, and that's from Ver. R is the distance from the wire. Now, don't confuse this with the radius where you have to cut in half. No, it's just the straight up distance from the wire. And mu naught is just a number, 4 pi times 10 to the negative 7. It's an awkward number, but just gonna have to deal with it, all right? So with that being said, let's look at an example problem and see how this would all work out in this equation. Okay, so this problem is pretty straightforward. They are asking for the magnetic field, which is B, that's what we're looking for. They want to know what it is, 0.2 meters from the wire, so that's our distance from the wire, and the wire is carrying 5 amps. So the equation that relates all that is just simply B equals mu naught I over 2 pi R. All right, and now we can plug those numbers in. B equals 4 pi times 10 to the negative 7 times 5 all over 2 pi, and the radius is 0.2. Now notice the pi's will cancel out. Now we can just go to our calculator, which I've already done, and we get 5 times 10 to the negative 6 Teslas. All right, and that's how strong the magnetic field would be 20 centimeters from a wire that's carrying current. Now notice it's a pretty small amount of Teslas, all right? But 1 Tesla is a giant, or is a very, very strong magnetic field, all right? So let's move on to our next equation. Okay, so in this scenario, we have our regular magnet here, well, with the North Pole, obviously the South Pole is on this side, and then we have a wire here. Now, what you have to view this is you have a magnet, and remember, a current is a magnet. So you have a magnet and a magnet. What do magnets do? They exert forces on other magnets. So this magnet is going to exert a force on this magnet through this one's magnetic field. So the idea is this one makes a magnetic field. This magnetic field then exerts the force on this. It's very similar to a proton's electric field exerting a force on the electron, all right? So what equation models this? What we want to figure out is how much force does this thing feel, all right? Well, the equation's pretty simple, all right? We've had Ver before. This is just F Bill, all right? And the F is just force. That's the force that the wire will feel, which is what we were kind of talking about there. B is a magnetic field that the wire is in. So B is this red line. Remember, the red lines are made by this magnet, all right? This magnet feels a force because it's in somebody else's magnetic field. And that's what B is. And L is just simply the length of the wire. All right, so let's look at an example problem and put this equation into play. Okay, so this problem is pretty straightforward. All right, they're asking us for the force. Let me get this thing in. There we go. They're asking us for the force. How do I know that? Because it says how much force. So they're looking for the force. The force. We know the length is 2 meters because it says the length is 2 meters. The current is 3 amps. Sorry, equals 3 amps because it says carrying a current of 3 amps. And the magnetic field is 5 Teslas. All right, because it says it has the magnetic field has a magnitude of 5 Teslas. So we're just looking for the force, so we plug that all in. F equals B I L, and we can do this in our head. B is equal to 5, I is equal to 3, and L is equal to 2. So 5 times 3 is 15. 15 times 2 gives me 30 newtons. All right, pretty straightforward and easy problem. Okay, in our final scenario, we're going to look at a single electric charge, and in this case, an electron. Now, the electron has to be moving for it to do anything. Remember, a stationary electric charge is not a magnet, so there is not a magnetic field. But an electron with a velocity vector, electron moving, is a magnet and can interact with a magnetic field. But there is a stipulation. It has to do with the directions of these things, and that's derived from mathematics. And we can see that in experiments, but nothing that I can show you here on video. All right, I can't do that demo. But the idea is, if we had this setup here where an electric charge is moving and goes into a magnetic field. Now this is something else is making this other magnetic field. All right, I don't know what it is and I don't care what it is. It could be a current or it can be like a regular hard magnet. But if the magnetic field in this area is in this direction, then this thing will experience a force. All right, this magnet here will feel a force from this magnetic field. However, if in this scenario, if the electron is moving through and enters this magnetic field, then it will feel no force. Now, what's the difference? It's all in the direction, all right? The idea is that the velocity direction, in other words, the direction that's moving, must be perpendicular to the magnetic field's direction. If you get that, you will get a force. If they are parallel to each other, there will be no force acting on it, all right? So let's see what the equation is, and then we'll look at a problem. Now, the equation that governs this scenario is just F equals QVB. Notice this doesn't take into account direction, so you're going to have to do that on your own by reading. Remember, if it's perpendicular, if V and B directions are perpendicular, then there will be force. If this and this are parallel, there is no force. All right, so you have to do that on your own. Once you determine that, then you just plug stuff in. Force is F is force that's acting on the charge. V is velocity of the charge. B is the magnetic field that the charge is moving through. And Q is from our electricity stuff where it's the amount of charge. And remember, that is in coulombs, which is capital C. All right? So let's look at an example problem and put these things into play. Okay, so in our problem, we have an electron moving east, and there's a magnetic field directed north. How much force will it feel? All right, so we have an electron. We have to know that Q is 1.602 times 10 to the negative 19 coulombs. All right. It says there's a magnetic field of 2 Teslas, and the electron is moving 1,000 meters per second. Now it also tells me that the velocity is east and the magnetic field is north. And we see that those two things are perpendicular, so this thing will experience a force, which is what we want to know. All right, so then we can just plug in some numbers. All right, we're looking for force. Move this up here a little bit. Force, we have 1.602 times 10 to the negative 19. That's Q. V is 1,000. And B is 2. And that gives us a number of, and I go to my calculator real quick. I go to my calculator, and that gives me 3.2 times 10 to the negative 16, negative 16, and that is in newtons. All right? So that's how we use that equation. Just remember, whenever you look at a charge moving through a magnetic field, you have to take into account a direction. Parallel, no force; perpendicular, force. All right? And that concludes our basic equations for magnetism. So now we can go use those for example problems and review problems, and we'll be all set. All right? Thanks for watching.